Good morning. My name is Ziyu Deng. I'm a current PhD candidate from NC State University. I'm working with open access to demonstrate the application to 3D design. I hope you use open access in your next application more because it's really useful and easy to use. Okay, 3D designs comes in many forms like C4 and TSV and flip chip die attach and die stacking. And 3D design is found in many forms, and which might be silicon on silicon, silicon on ceramic, FR4, silicon on layer, 3D chip stacks, and memory cubes. And those are very popular design styles currently. And we already have lots of product. We've seen a lot of products in there in the market, especially in the AI accelerated chip. But what is the 3D challenges? It'll be easy to make a sum of all parts, arguments indicating good chips combined to make a good system. This might work in a simple case, but we push technology, it can easily fail. In two tests, all the chips are tested before assembly. In two timing, how do we add parasitic RC to the system netlist or the two development? These are all the very common 3D challenges. Maybe timing, simulation, test, and maybe thermal, it will add up some heat and the mechanical engineering chip, that also very important. Some applicable open access features will be complete hierarchy support, module domain, which is logical, and block domain, which is physical. Synchronous with the properties are on the same net, and coordinate translation will be the OA transform we'll get there later, which is very important. The transform between the user unit and the DBU, which is database unit, which is also very important, because different technos with different scale, that is the key part to reflect the data into the real world scale. The abstract support, including left and depth, also support that. And adopt and release tech files, which will allow the application to change tech files as needed. Commonly used for multiple library sources, which you might have different dies from different tech nodes in one 3D design. Especially common in the HBM application, which you will be stacking a lot of memory die on one big substrate, and that will be used as a high bandwidth memory. And extendable data, which will be add your own data tag and add your own classes. These are the current feature we support. All of these features are also available in Python, Ruby, and Tcl, which is very easy to use and very simple. For the 3D demonstration, I have made this example based on the Python API of the open access. Here is the flow of my software. It will start by creating a hybrid library, creating a new library with no tag file and attached to nothing. And we will create a new layout cell view, which means we will have a new design. In this moment, we will add an instance from lab 1, technology 1. In this operation, we will attach our library to the first library. And after we add instance from that, we change attachment from lab 1 to lab 2 so that we can add instance from a different library with different techno, which in our example is from FreePDK45 to FreePDK15. And we also have a FreePDK3 as example here. And in the end, we save the layout. How to show that we have accomplished this? So in order to do this, I have an example tool, which is very simple, made in Python, and it will have some basic operations that can show what we have done in here. Key functions will be make tag. It will read the tag from the hybrid library. It will create a render CSV file that it will have all the colors and the hash settings for all layers. And we use make shape to show what kind of layout cell view we have created using this layout here. We'll show you that later. This is an example of tool made based on the open access API on Python, which is very simple to use, and you really need no additional package to use that. And let me give you a quick example. Here we have a library which based on which I made it on my own, and let's do a make lab. And here you can see it shows you all the cells here, and the cell view on the right side. It tells you which cell has which cell view, but in a very clear way. Like if there's a marker, then yes, there is. Very straightforward. And we also have another function which is make tag, and it will tells you what tag library. This is another. Right here. This what tag node this library use. Like you see, this ERD3 lab is based on the NCSU 3PDK3, and it will read out the library my library which is attached to. Like it will shows you the DBU per UU, the resolution, and the user unit, which is very common stuff, and layers, and with numbers and names, layer numbers, and materials. And their purposes like drawing, fill, shot, and text, something like that. And there are no vias out there. And it will create a render attributes, which we will use that later. Because open access currently do not support the render like for example, if you want to have your metal 1 layer be drawn as blue, open access currently do not support that. So we create one like this. Let me open it in CSV like this. The all the layers here are kind of pre-filled with some random colors, but some common layers are marked with some common colors, like the gate or poly in red, and metal 1 in blue, and metal 2 in pink, which is gonna be differences between those metal layers. And let's go on to the third function, which is make shape. And let me go through a very simple layout from the shape. Give me 1 second. Yes, okay. This is my handmade inverter from my coursework, and let's show the shape. This is the shape of the layout shape image from the layout from the cell view inverter. Well, as you can see, it's very straightforward with the power and the gate and some metals out there. Yeah. That is a very simple tool. And how would this connect to this to the 3D capability of open access? We'll get there. The core of the 3D IC is about managing different tech nodes. And to do so, first you need to dynamically change the tech node on the. There are two options that you can do while managing different tech nodes. First is change the tech node on the fly. The second is have a hybrid merged tech nodes, which will include all the necessary nodes that are there. And I will give a quick sample of that. Let me go into my hybrid library, which is here. Make clean so that we can start from fresh. And let's do make. Here we are. I have just created a new. Let me do this. Use the clean. We have a new make. Okay, right now I have made several options, several operations. First is I create a new library, which is hybrid library, hybrid lib. And the second is uh, apply three different instant, each from different library with different node. As you can see here, the new cell will create it, which is a layout basically. First, it first it will uh, create first the first instant it applies from the NAND gate 45 library, which is based on FreePTK 45. As you can see here, library open, attachment to another library, true, and tag NAND gate 45 open. Right now, this hybrid library is attached to NAND gate 45. And when we apply next instant from a different library, it will switch on to NAND gate 15, which is based on FreePTK 15. And the third, which is created based on the net FreePTK 3. And I will show you the code of how to do this. See, okay, see here. Okay. Okay, here is where we open the libraries and we attach a Techfile to a new library. Here, let's see. Range, attachment. Right, okay. Let's add a cell from library to attach one. We applied an instant here from the NAND gate 45 to here to a position here. And we switch our library here. This is our current library object, and this is just attached to another library. Very simple, just one line of code. And after we make that attachment, we can apply an instant from the second library, and so on and so forth. We can do the same to the third one. And how would this be looking at in the real? We can go back to our tools example to show this. Let me do some little twitching here. First, let's only see the top hierarchy, which is the top block. Let's use the make shape. Okay, 3 instances here to be shown. This is what we have just created from that code. Here, the I0, which is from NAND gate 45, is the first instant that applied from the first tech node. And this is the second instant from the second tech node. This is the third. This demonstrates that the open access library management are able to manage different instances from different tech node, which is very useful in the 3D design, because you might gonna need to have some base die made on a tech node, and maybe some other HBM memory to the stack from another company, which use a complete different technology, which is a very popular design style right now. The other stuff that is important that the open access have the ability to demonstrate the different layers from those. And I can change our knobs to show all the hierarchy there are. And let's do it again. Make theme, shape. It will take a moment. Okay, this is the part that You can see here is just a simple cell from the NAND gate 45, which is based on the free PDK 45, first tech node. And the second here, this is from the second tech node, which is free PDK 15. And this is free PDK 3. Through this very simple example tool, we show that the open access has capability to manage different instance, also manage different instances inside those, and we can use OA transform to carry the relative coordinates and the and the and the orientation to the top to the next level, so that when we try to plot those into our layout image, we can have the correct orientation like those. So let's go through the most complicated example 2 here, which is the read shape. The first, it will begin at find the beginning point. Yeah, here. The main function start here. First, it will just read in the infos from the make file, which is here. If it doesn't, it will just read in the default example right here, and it will open the library as shown here, and read in the render file. We have to just create from the tag file, which is like quick reminder like this. This is how we're gonna plot stuff, and it will count all the shapes and instance like here. This is the read tag file. It will recount all the shapes and instant, and here get a count, and next it going to a function to find all shapes using the OA layer purpose pair header. It will do stuff in the flow. It will do is it loops through all the layers and finds through all the purposes. Is there a pair that match? Is there a pair that match? Yes, then we go through. Are there any shapes there? Yes, then we keep finding those. What type of shapes are there? Maybe a polygon, maybe a text, maybe something else. If there's a polygon, then we record the point list, which is you're gonna need a point list to describe a polygon. And if there's a text, we record the B box, which is just a rectangle, and else others will be recorded in else. Are there any loops? No, then stop. Then we stop looping all the purposes and we go to the next layer. If no more layers, then that's it. A very common a double stacked for loop. In the end, it will generate a list like this. This first layer, first purpose, any shapes, any kind of shapes out there. Yeah, all the shapes info are stored in there. And the next step will be very similar to find all the pins, which is out here. Which is similar, which it will find all the pin name, type, is their placement, terminal name, terminal position, net, and pin box. Let me give you an example of this. Where's the box? Okay, in this example, there's no pins. We can make a very quick example to show you how the pins might be looking. Okay, here's the example of what the shapes will be, like shown in here. The pin name, the pin type, is their placement, the terminal name, position, which is basically the purpose number, and the net. And right, start from here, start plotting. We'll first create an object using the matplotlib, which is very basic, and it's also already been included in the OA packages. It will plot in first. It will go plot instance. Then let's use this all the present. Here is the all the plot background setting, and it will start looping from all the instance. And there's a knobs here that if the show all hierarchies settings, which should be setting in here. Here, show all hierarchy. If this part is set to 0, then no, then plot the instance with only PR boundary, which will be the first kind of a hybrid layout you saw with only the instance name, the orientations, and the PR boundary, which is only the rectangular of the instance, and draw that. That'll be finished. And if we choose to show all the hierarchy, it will be eventually like this. It will go through all the shapes within all the instance out there. To do this, we need to use the OA transform, which is the method that we use that we carry out carry the relative coordinates and orientation to the next hierarchy, which is let's go through. It will start a function here. That's those. Yeah, started from here. It will read cell info in and the upper transform, which is the orientation info. Like that, and check the current tag library here. If it doesn't match, then it's from a different tag. We will attach to a different desired library. If aligned, read. If not aligned, change the attachment, and now we are aligned. And we read cell info and upper trans, which will let's see. Yeah. It will read the shapes under this block and apply the upper transform. And after this step, the shapes is now an the absolute orientation. Because if we only read let's say this for example, if we only read the polygon within this instant, we will only get the relative orientation. And if you got a instant which is facing downward on the top block, and in the cell library that instant is naturally facing upward, then you need to flip it over, which is what this OA transform is doing right now. And right now we have an absolute step. We have absolute orientation. And it will iterate to all the shapes we have, and find all the shapes and sort it into a list. And here is and here is this function that search if there is lower hierarchy, which is is this block still has some instance out there. Well, if yes, then we calculate the combined transform for this instant and carry out to the next hierarchy, which has been done in here. The upper level transform information will combine with our current block and generate a new combined transform, and use this as the upper transform for the next hierarchy, and we can continue this cycle. And so that we can have all the shapes in the right position and the right facing. And the function will recurse on itself until we reach the leaf cell. How do we tell we have reached a leaf cell, that is no instance anymore? Then yes, we are reaching the bottom. And after all the instant shape are finished, we leave this loop and plot the shapes that is on the top one, which most likely will be wires. And and that part will be starting from here. Start plotting shapes, and if there's a polygon, draw things like this, and use the same colors from the render file for both edge and the facing. And if there's a text purposes or similar, we will only draw the edge, not filling it. And if else, most likely will be a pass or a B box. Both are treated similarly as a B box. We'll draw a rectangular there. Other purposes will be treated similar, like the text. And okay, next we'll be plotting pins and finish functions. So there's the pins. Pins, yes, the pins are here. Will be shown in white and have some labels out there, which will be like this in white, and it will be very easier to figure out what kind of stuff it is. And that's pretty much all the functions you do, and we'll have some knobs that will change the step, which is the step of here, the label, the length of each of the grid. That is the most of this example tool. The same, it use a lot of functions in there. It will use the change library attachment and OA transform, which is the two most important function there is in open access. Okay, that's the example tool. After all this demo and the summary of this, the open access is a very good choice for developing a 3D application. It supports top-level HDL like Verilog. It enables test vector generation at the system level. When your logic is good, you can expedite physical design. We have netlist ready, constraints still apply, and logic change can be made more easily. And we have existing chip-level applications still apply. Collaborate with developers who already have open access 3D applications. Will make open access code. This is what the coalition does. The cost of developing a common solution is reduced. Hope you like it, and thank you.